Hello, team, ladies and gentlemen. Welcome to this month's webinar on how software fails. So, obviously, that's a big topic, and we're not going to go into every single way software can fail. And there's somewhat of a philosophical debate which will never be solved or resolved satisfactorily to many that suggests that software never fails because it does exactly what it is told to do over and over again. We've never found software where the instruction was to add 1 plus 1 and it returns a 2. Now, in computers, there are genuine circumstances where you need to add a couple of numbers together, 1 plus 1, but computers don't store numbers the way we would like them to. We use decimal numbering systems, and computers use binary numbering systems. And that gets really tricky when we're talking about decimal things like decimal places. In the earlier Iraq War, this came to bear when the Patriot missile, which is supposed to protect against incoming missiles, well, there's a circumstance where it did not do that. And it turned out the reason being is because the Patriot missile software records time by adding up 0.1 of a second over and over again. So I have this big integer, which could be thousands, in the order of thousands, 10,000s, and that meant that was a clock that allowed the Patriot missile to keep time. Now, anyone who knows anything about software and binary digits is that when you deal with decimals, it's never perfectly accurate. In fact, when you have to define how many binary bits you use to define numbers that we think are really easy to quantify, especially 0.1 of a second. And when you store 0.1 of a second using binary code, it's actually not quite 0.1 of a second. It's a little bit more than that. And so you add it up over and over and over again, and all of a sudden you'll have a clock which is about half a second out of reality. Why is that a big deal? Well, you can imagine how far a missile can travel in half a second. Now, if you're half a second out in terms of trying to intercept it, you are hundreds of yards or hundreds of meters out of the picture. And it's exactly what happened. Essentially, the Patriot missile, when it was asked to look for the incoming target, it looked in the wrong area, about a few hundred yards or meters off. Didn't see anything, didn't launch, and unfortunately didn't protect the barracks in northern Iraq. And so some people might say, well, that's not a software problem. That's not a software failure. That's the software doing exactly what we asked it to do. And yet we can go around the buoy that many times on what software is and isn't supposed to do. But in the world of reliability engineering, we cannot get hung up on semantics. And so software failures are loosely referred to failures that emanate from the software domain of your system. And the reality is that most nominally hardware systems these days are just as likely to fail due to software. The camera that I'm looking at right now, it's a digital SLR. They used to be an SLR only. So what looks like a hardware product is actually just as reliant on software as anything else. Thermostats, just as reliant on software as anything else, and we'll look at that today. And so with that as preamble, we're going to look at how software fails, and I'm mainly looking at you hardware people, you mechanical engineers, you designers, you manufacturing technicians, because this is unfortunately where a lot of software-related issues start to happen. So software right there. So software runs everything these days. The counterpoint to that is that if software runs everything, it also means software ruins everything as well. Software is able to cause failures like never before. A simple coding error can take out an entire fleet of things versus what our largely mechanical or hardware-centric brains tend to think of. If we don't tighten a nut properly, well, that affects that vehicle or that machine. If we have a defect or bug in our software, that can take out an entire fleet of equipment. And so software failures are extraordinarily challenging to deal with after they happen. They're very hard to uncover, and 9 times out of 10, when we're doing root cause analysis of a failure, there is a rush to look at hardware first. Look at how did this thing fail due to hardware, hardware. And only after we exhaust all those hardware-centric issues, then we start looking at software. If we start looking at software from the very start, perhaps we could have saved months, years, millions of dollars, a full recall, and so on. So, for example, this is for those of you who are veterans to my webinar, you know that I use a smart lock as one of my sort of exemplar systems. Now, a smart lock is a wonderful device. It's a great exemplar in terms of containing traditional mechanical technology that is now merging with smart technology. So this smart lock is just as reliant on software as it is on hardware, and you could argue, in fact, it is more reliant on software. And so when software fails, what we are looking for are coding errors or bugs or defects. Now, you might notice these are human. So in reality, software will fail as a result of a human error. We don't code it properly. We introduce bugs or defects. So coding errors, bugs, or defects, are synonymous. Depending on which industry you're in, you might call them one of those three names. Regardless, they mean the same thing. So when it comes to let's just say a failure event, so we have some sort of system fault or failure, as I mentioned, we tend to think of hardware first. Nissan very famously, during an issue with its airbag non-deployment for the passenger seat, it moved heaven and earth to examine why the passenger airbags weren't deploying in their vehicles. It had a recall. It looked at the sensors in the passenger seat, which are there to detect if an adult human is in that seat and therefore turns on the airbag on the passenger side. It identified a manufacturing issue, and it didn't know if that was causing the problem, but it issued a recall anyway, replaced all the strain gauges that detected the weight, still had issues with airbag non-deployment. They then conducted tear-downs of vehicles that consumers were complaining about not having those airbags deployed. It couldn't find a problem, and so what did Nissan first conclude? They concluded that passengers were sitting in the seat incorrectly. So let that one sink in. The one thing human beings in most third world countries are really good at doing, it's sitting. And so to suggest that the airbags weren't deploying because people weren't sitting properly, it just goes to show what happens when we think we exhaust all hardware problems. But the issues kept coming. And it's a safety-related issue, so they had to keep investigating. And they eventually found it. They found that the problem was that if in these vehicles around about 2012 to 2016, if you turned the car on, if you turned the engine on, so it was idling, creating a vibration throughout the entire vehicle. If a passenger hadn't already sat in the passenger seat, so instead the car gets turned on first, and then the passenger sits in the passenger seat. Well, the software was then already auto-tuning, so to speak, the vibration out, and it also then filtered out any subsequent adult sitting in the passenger seat. And so it was an issue with software all along. It took a full recall to fix a problem that didn't need to be fixed. It included full teardowns of vehicles, which are very expensive, as you know, and it involved a very embarrassing edict that passengers weren't sitting in the seat correctly. Ultimately, it was software all along. So in this day and age, we need to be very careful about rushing to judgment when it comes to root cause analysis in particular, because of all the potential root causes out there these days. Some are absolutely going to be from the hardware domain, and the others are going to be from the software domain. And they are equivalent from our perspective. One is neither more dominant than the other. They each have different characteristics. But just be aware, human beings are very mechanically oriented. Even the software engineers amongst us, we live in a physical world. We might argue we live in a digital world, but in terms of how we get up in the morning, we live in a physical house. We walk down physical stairs. We drive physical cars. We drive around physical trees to make sure we don't hit those trees. So our brains are wired to think of the physical, and that can sometimes bleed over into our engineering thought process. So software is a set of instructions called code that tells a computer what to do. And so if there's anything wrong with software, it by definition is a problem with the instructions that we come up with to tell that software what to do. And so what I'm going to start with now is a conversation about what most people think the root cause of software failures are. Specifically, our software engineer here. So a lot of hardware engineers simply think if software has failed, it's because this person stuffed up. Now, I'm going to try, so actually the main point of this webinar is to burst that bubble. The biggest source of software failures is the hardware engineers, the designers, the technicians not telling our software engineer what that thing needs to do. Not telling our software engineer that the software needs to take into consideration the vibration of an idling engine when it's detecting if an adult human is sitting in that passenger seat or not. Another big root cause of these failures is just a slight variation on not telling them. It is telling them too late. Just show of hands, digital hands. Who has heard of the agile software development process? So quite a few have. So agile software development, what does that mean? It involves a number of sprints where at the start of a program, project, call it what you want, we have a software challenge. The software engineering team focus on doing bits of it at a time. So the very first sprint might involve, I don't know, it might be the algorithms used to detect if a human's sitting on a passenger seat in a vehicle. Another sprint could be the user interface. Another sprint could be the interface with the actual warning light on the dashboard. Another sprint could be sending the information to the airbag mechanism. All those different things. That different parts of the software are broken down in different chunks, and then the software engineers will focus on developing those chunks. Actually, I should start over here because as you see it from right to left, so left to right. This represents earlier in time. So I'll try and do that. So the first sprint is where they take a bunch of functionality, code, get that functionality right, and then move on. Now, if I highly recommend the work of Anne-Marie Neuffelder in this space, who is the patron saint of software reliability. And when you do any sort of software coding, you will always introduce defects. Now, there are things you can do to minimize the introduction of defects, including having a robust, for example, agile strategy, having design tools, which we'll talk about later on. But anyway, so the first bunch of code that gets written will have a number of defects. And in the agile methodology, we have a period of what is called defect discovery thereafter. And statistically, we can see when the defect discovery peaks and then starts to go down through testing. And once you hit the peak and start to go down, you can then calculate the remaining number of defects you are likely to have before. And once you are confident that you've hit, say, 95% of defects that you discovered, you then move on to the next sprint. And there's actually a bit of science behind it, which allows you to schedule the sprints in terms of number of people you need to have. In fact, be careful though, Anne-Marie has also discovered that if you have too many people involved, it actually makes it worse. She's also discovered that too many people with PhDs make it worse as well. So the idea is that if you were to look at the the defect rate or failure rate. You do a sprint, defects go through the roof because you're writing new code. Defect discovery, failure rate goes down, 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 down. Then you get to an acceptable level. Then we do another sprint again, down, 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 and keep going. So why am I boring you with this discussion? Well, imagine you're a software engineer who's carefully created an agile strategy, and you've got a number of sprints. So you go, okay, I need to do this bunch of code or this functionality. Sprint 1, sprint 2, sprint 3, and you allocate all the time for testing, defect discovery, and you're on top of it. Now, let's just say the hardware engineers, middle of the way through the third sprint, say, oh, we forgot to tell you that your software needs to also do this, that, and the other. Which means that the code which we thought was good in sprints 1, 2, and 3 now need to be rewritten. So if you want to destroy the reliability of your products, don't tell your software engineers anything or tell your software engineers what they need to do after they start coding, because they then need to go back and essentially break down what they've already developed, already tested, the defects they discovered. They don't have any more resources to do all the testing. So you add all these defects without them able to discover those defects. And now they are behind the 8 ball for the rest of that agile process. And so again, I cannot stress enough, if you want to doom your software dependent system to failure, either don't tell your software engineers how the hardware works, or if you do, just wait. It's a great way to destroy reliability. That sort of scenario is behind the overwhelming majority of software failures. It's not due to this lady here, the quintessential software engineer. So let's look at what I'm actually talking about. So us hardware people will tend to look at a system like this. We have a pump on a pipeline, and we can sort of visualize this. Fluids moving from one direction to another, great. An impeller blade might wear out, the pump stops working. Very easy to visualize and understand. But in the world of software, we don't have a physical thing. We have code. So here is code. This is not an unusual sort of code. This is called the bubble sort procedure. It is what we call a sorting algorithm. So what does a sorting algorithm do? Well, here is a bunch of numbers. We have 6 numbers on the left. They are not in any particular order. The sorting algorithm is supposed to take these numbers and then output them from smallest to largest, as you can see on the screen right now. So that's what a sorting algorithm is supposed to do. How do these lines of code do that? This is a very well-known sorting algorithm. You can see we have 13 lines of code. And what those lines of code do is instruct the software to look at the input numbers. And here we have the input sequence of numbers. The very first thing the software does is examines the first pair of numbers. You can see we have a 7 and a 3. Now, if that first pair of numbers is not sorted, that is, the first number is larger than the second one, the software then asks the computer to switch those 2 numbers around. Fantastic. So 3 is smaller than 7. We're off to a great start. The next thing it does is then look at the next pair of numbers, 7 and then an 8. Fantastic. Doesn't need to be rearranged. Next pair of numbers, the 8 is larger than the 5. We need to swap those 2 around. Okay. Next one, swap those around as well. And last but not least, the last pair, 8 and 9, is already sorted. And so here is our next iteration of sorted numbers. You can see we're not there yet. You can see, for example, the number 2, the smallest number, is 4th in line. It needs to be right at the front. It's the smallest number, so it needs to come first. The 7 and 5 are also the wrong way round. So what happens with the bubble sort procedure is then it starts again. It looks at the first pair of numbers. Now, if that first pair of numbers is already in the right order, the software asks the computer to remember this and will represent this memory with a check mark, a tick. Then it moves to the second pair of numbers. They're in the wrong order. Software asks the computer to remember this, but in the wrong way. It essentially registers a cross that one of the pairs of numbers was not sorted. And then it keeps going through until we go back to the start. Now, because it detected at least one cross in its previous iteration, the procedure keeps going. Check, oh, another cross. And you can see how it keeps going through until finally it will look at all those pairs of numbers. They'll be in the right order, check marks all the way, and we are now done. So if you've understood that, well, you've understood how that algorithm works. So that's what these relatively small numbers, small lines of code do. Now, the software issue, the software failure that most people think of is something like this. Here is the line of code where the computer is examining the order of numbers in that pair. So this is saying that this line of code is asking the computer to identify if the first number in a pair is greater than the second number. And if that's the case, it needs to be swapped around and have a check mark registered next to it. Let us just say that our software engineer makes a simple keystroke error. Instead of a greater than sign, we have an equals to sign. So this is the sort of thing that we think of as software failures. It's supposed to be a greater than sign, it's an equal sign, the decimal place point is in the wrong spot, the variable is misspelt, etc., etc. This is what most hardware manufacturing technicians think of. Now, let's just say that this, I should be coming up in a tick. Let's just say that this code has that bug, that really simple coding error, then the code won't sort out the numbers at all. It will then have the numbers come in and the numbers leave in the same order it received them. But here's the thing, coding errors are really easy to fix. They're really easy to find. They don't require a whole scale decomposition of the code and rebuilding it up from scratch. And less than around 30% of all software failures are based on simple coding errors like this. If all our software failures were based on simple coding errors, software would be borderline, perfectly reliable. These are so easy to find during arbitrary testing, so easy to fix, that they do not trouble a good software development process at all. But the hardware engineers amongst us assume that this is the dominant way that software failures are caused. And it's not true. And we'll examine that reality in another example. So what you're about to see on the screen when it eventually comes up is an HVAC system. This is an HVAC system typical of North American houses where we have a furnace in a basement usually. It's also connected to an air conditioner with a heat exchanger outside the house. But this big thing which has gas, which is supposed to heat a residential house, unfortunately, it isn't heating anymore. So an HVAC system, of course it's a hardware system, right? Look at it. You can touch it, it's big, it's chunky. So if this thing isn't heating anymore, well, there's all sorts of reasons as to why that might be the case. And for veterans of my webinars and courses, I use what we call the tree of failure to represent the causal chains from the failures represented by these apples at the top. The bigger the apple, the angrier that failure is, or the more severe that failure is, down to the root causes at the bottom. Now, during root cause analysis, for example, we are presented with an apple and we are trying to find the root cause of that failure. Now, when I say root cause, I should more correctly say root causes. It's very rare to have a single factor that results in a failure. Now, that might seem like an unnecessary complication, but it's great. If you can identify a number of potential root causes or causal factors, you can then pick and choose which one's the easiest ones to address. And we want to make sure that during root cause analysis, won't get into this in too great a detail, But we don't want to be too legalistic. So, for example, if we do a root cause analysis and identify that there was a hardware fault in our systems, some organizations will insist team hardware, you go fix this. This was your fault, your problem. It's up to you to make this better. However, a more mature organization, which isn't all about blame, might first ask the software team, hey, software team, is there anything we can change to the code to address that hardware issue, which has now now exists in our entire fleet of equipment, for example? We want to explore that option, hardware fault, so to speak, or hardware to blame, but maybe the software team can easily address it. Vice versa, you might have a software issue. It just might be easier for the hardware team to address it. So that's why we don't want to be too legalistic about the root causes of failure. You want to come up with as many potential contributing factors as possible so you can pick and choose the ones which are the cheapest and easiest to address. Now, the tree of failure that I historically use has been our hardware tree of failure, which has its own set of questions about how something failed all the way down to root causes. So, for example, if we have our HVAC system for our hardware tree of failure, we might ask ourselves these questions during a hardware-centric root cause analysis. What is my system doing or not doing? What is my component doing or not doing to result in my system not doing what it's supposed to do? What does the broken bit in that component look like? How did that broken bit break? What started that? And what are the root causes that allowed that thing to start to exist in our system? So for our HVAC system, an example could be that because the HVAC system doesn't heat, when we do root cause analysis, we might brainstorm at the component level that the furnace might not be igniting. Brainstorm, brainstorm, brainstorm. What does the broken bit look like to result in this? Well, the flame sensor is bent. The flame sensor detects if something is burning in that furnace. If it doesn't detect flame, it shuts off the gas. So the flames, and that's to prevent gas flooding the house without it being burnt. How did our flame sensor break? From shock overstress. That's a failure mechanism. What started it? Well, caused by an assembly drop when it was being put together. So here we have answers to our questions. And once we have these answers, it's really easy to then identify potential root causes or perhaps jump straight to the corrective actions to try and mitigate a potential assembly drop. Now, of course, during a root cause analysis, when we're brainstorming, we're just coming up with potential or plausible scenarios. We don't know that this was caused by an assembly drop. But that's not the point of some of the more detailed root cause analyses during the early stages. We want to start by trying to understand what could happen to then target our investigation thereafter. So we might investigate, was the flame sensor bent? Oh no, it wasn't bent. Okay, so this scenario can be ruled out, but it helps us really target what we're looking for during any subsequent failure analysis, inspection, or forensic review. So that's what the hardware tree of failure looks like in terms of questions and answers from top to bottom. But software is a little bit different. Now, our HVAC system is going to be controlled by a thermostat. Now, this thermostat here, for anyone who is younger than an arbitrary age that represents age, or the elderly. Oh, sorry, I really messed that phrase up. For young people out there, this is an analog thermostat. An analog thermostat has no software in it. It has a couple of switches, has the modes, has the fans. You can see the fan switch is either on or automatic. Why is that? Well, if the temperature drops low enough, then this analog thermostat will send through its signal wires a couple of commands, a couple of signals, one through the heating wire and one through the fan wire. And the signal through the heating wire tells HVAC system to turn the furnace on, and the signal to the fan wire tells the HVAC system to turn on the blower fan. So let's look at what that means in our HVAC system sitting in the basement of our house. Going to come up any second now. There it is. So there's the HVAC system. This is what it looks like. So let's take the covers off and look inside. And this is what most HVAC systems in North America look like when there is a furnace involved. So once there is a signal to turn on the furnace, the gas burners will ignite, having hot air passing through the heat exchanger, which then exhausts outside the house. So that's the first thing that's going to happen. The second thing that's going to happen is that signal to the fan is going to ask the blower motor to then suck in air through the intakes and blow air through the heat exchanger, which then heats and is passed into the house to warm the house. So that's how a furnace works. Now let's just say that the blower fan isn't turned on, so the heat exchanger is just going by itself. Well, that could be a problem because if there's no air blowing across the heat exchanger, this will get very, very, very hot to the point that the metals might actually fracture, allowing toxic gases to now seep into the ductwork in this house. So that's a bad deal. We never want to have a signal to our HVAC system where heat is commanded but not the blower fan. Now, to be fair, most HVAC systems attempt to have a fail-safe built into the hardware to shut down the furnace once it gets too hot, but fail-safes are not 100% perfect. So in a scenario where the fail-safe doesn't turn off our heat exchanger, we have a problem. So you never want a thermostat to ever command the heat without commanding the fan. So analog thermostats are great at doing that, making sure that only ever turns on the heating when it turns on and the fan at the same time. The reason being is because it's 100% hardware. There's mercury switches involved, relays, transistors. It is physically impossible for the analog thermostat to be in a state where it's commanding the heat but not the fan. And of course, someone might be saying, hey, you could have that fan wire disconnected, got that, or the fan wire is shorted, got that. But in terms of the design itself, there is no conceivable state where electricity can flow to heating, but not the fan itself. So we can never have a scenario where the fan does not receive a signal from our analog thermostat. Smart thermostats, that's very possible because everything's controlled by software. The software controls the states that the thermostat is in. And so it's very plausible for a software defect, a coding error, a bug to result in our smart thermostat commanding heat while not commanding the fan. And so that could then cause our heat exchanger to heat up, fracture, and not work at all. So during root cause analysis for why our HVAC system is not working, we need to use our software tree of failure to get to the bottom of it as well. So once we look at hardware, we often then look at software. Now, when I'm conducting root cause analysis, where the software is part of the deal, I typically ask the team to brainstorm hardware scenarios first and then brainstorm software scenarios. We allocate roughly the same amount of time for each, but I find it's very hard for engineers to sort of switch between the two. So if I ask everyone to focus on hardware first, or hardware first, no, what's right? There we go, hardware first. Even the software engineers in the team can start focusing on how, solder joints this and you maybe gas line that. Okay, now once we've exhausted that, then we move on to software. Everyone thinks of software failure scenarios. And a lot of the software failure scenarios, again, exist the interface between the hardware and software domains, emanating from the instructions the software engineers get, or perhaps the software not being written in a way where it can accommodate all the different hardware states. Now, one of the issues that Anne-Marie keeps pointing out is that in this day and age, users expect software to deal with everything. What do we mean by that? Well, in the olden days when we had analog thermostats, consumers were much more comfortable, perhaps it was just a different genre of people, to deal with and fault find and understand the physical reasons why something wasn't working. But when we have software, especially if your product has the word smart in its title, what does that mean? That means the user expects that that smart whatever is able to detect hardware fault states, able to detect if something's not quite right in the system. Users and customers these days perhaps subconsciously expect, but they still expect it, software to deal with everything. And so we can't just simply go, oh, well, it's unreasonable for the customer to expect it. No. If you've got a smartphone, you expect the smartphone to do everything from manage battery life to telling you if you've left your torch, your flashlight on, to alarms this, and you expect your smartphone to essentially do everything that the Nokia 3210 didn't. So when it comes to software, we need to bear that in mind. So the software tree of failure, which has its own set of questions, which differs from the hardware tree of failure, those questions look a little bit like this. The first question stays the same. What is my system doing or not doing? That's the system failure mode, system functional failure mode. That won't change for our hardware or software systems. So for example, HVAC doesn't heat. Same answer to that question. But when it comes down to the next question, what is my component doing or not doing? In the software tree of failure, well, it is what is my software doing or not doing? And you might have different software programs. So what could be a plausible explanation? Well, my software is commanding heat without commanding the fan. What is wrong with the code to allow this to happen? This is that software bug, those software defects, those coding errors. But remember, simple coding errors account for less than 30% of software failures. They're really easy to identify, they're really easy to pick up, and they're almost certainly not going to be the reason why your thing isn't working. And so I'm going to introduce a term which makes some hardware engineers' skin crawl, as there is a race condition. Oh, good Lord. Sometimes we hear about this race condition. Some hardware engineers nod their heads and say, oh, yeah, race condition, I know what that is. But we have these software-specific defects which go beyond simple coding errors. So what is a race condition? A race condition exists where software is trying to execute the same function but at slightly different times. So for a smart lock, remember that smart lock at the start? A race condition could be a smart lock receiving a command to lock from a user through a smartphone and a user through a computer in the house where the smart lock exists. So let's just say that fortuitously, or maybe unfortuitously, these two people send the command to lock that door at almost the same time. Let's just say there's 5 milliseconds between the times by which the software receives those two different commands. Now, software can be designed in a way to make sure those race conditions don't start. It can be designed in a way where any locking sequence has to be completed in full before the next command is processed. So for example, if in that smart lock, the lock attempts to execute both locking commands at the same time, the second locking command that comes halfway through the first locking execution might have the effect of reversing that first attempt. Why is that? Well, when a lock receives a command to lock or unlock, it usually tells the lock, okay, insert or retract the bolt. And after it's done that, it then changes the variable in the software code to locked or unlocked. So if the second command comes halfway through the first one, what you risk doing is sending two signals to the motor. The second command looks at that variable, sees the lock isn't locked yet, even though it's in the process of being locked. And so when the software executes the second attempt to lock, current gets sent to the motor and it might inadvertently now pull that bolt back out. The smart lock then records that lock as being locked, even though those two commands have essentially locked it and then unlocked it in the same breath. That's a race condition, and it's really easy to identify them if you design your software properly from the start. And that's where software engineers need to be aware or told by the hardware engineers that it's possible for these commands to be received from multiple sources. If it's only possible to receive one command from one source, race conditions aren't the biggest deal in the world. But if you can get multiple commands from different sources, race conditions may be a problem. So how did this race condition get into the code for our smart thermostat? Through software design. So it's not a simple coding error. And this could be down to the team's decision to not create what we call a state chart and failure to test for hardware fault conditions. There certainly are scenarios where software engineers are told by the hardware engineers what the software needs to do, and they don't do things like create a state chart. A state chart is a really great tool to essentially show the different states a system can be in. Anne-Marie explains it like this. The shapes in a state chart represent what the hardware is doing at that point in time. Arrows between those states represent how the software commands that hardware to move from one state to another. And there are some variations to that theme where sometimes software itself is doing things like calculating a number, and that number then becomes a state itself. But having a state chart creates a great visual interface between software and hardware engineers to look at the same diagram and interrogate if that's how they want the product to behave. And so here is a software failure scenario where the root causes are failure to create and design a state chart, there I'm back, and failure to test for those hardware-specific fault codes. Johan writes, state charts sound like something as important as free body diagrams for stress jocks like me/you. Absolutely. And a lot of hardware engineers tend to shy away from state charts. Oh, it's a software engineering tool. No. There's no reason why a hardware engineer can't develop a state chart to then explain to the software engineers what the software needs to do as a result. It's a great way of just making sure the ambiguity is removed. It's a fantastic tool. Lots of failures have occurred because people don't write state charts. A very fertile breeding ground for this sort of failure are those highly corporate organisations which contract out and farm out different parts of the code or different parts of the hardware development to subcontractors or different groups and different silos. Everyone's doing their one thing, not looking left, not looking right. And this fertile breeding ground for things like race conditions where no one has a state chart to sort of then have that common Rosetta Stone, touchstone reference to explain to everyone what we're supposed to be doing. So software is the failures are rarely caused by this person here. Now, again, if you want to ruin the reliability of your product, don't tell her what the hardware is going to do. Don't tell her the fault conditions of hardware. Think of going back to that thermostat. Don't tell her what a faulty temperature sensor might look like. A very classic example is if you have a third-party temperature sensor which smart thermostats communicate, what happens if the reading from that third-party temperature sensor hasn't changed for 3 days? It stayed at 72 degrees Fahrenheit or 22 degrees Celsius for 3 days, hasn't moved one bit. Now, one plausible scenario is that it is in a root cellar or something 3 miles beneath the earth where the temperature never changes. Or it's broken. It's beyond implausible for a temperature sensor to not change 1 degree for a period of 3 days. If we see that on a chart, we would ordinarily assume that temperature sensor is broken. That's a relatively well-known hardware failure mode for that temperature sensor. We have to tell the software engineer that's what a broken temperature sensor looks like. Once that software engineer gets told that, he or she is then able to incorporate that sort of diagnostics into the software to, one, ignore that reading that doesn't change for 3 days, and two, tell the user that there might be a problem with that sensor. Whether we like it or not, whether we think whether we're designing a smart thermostat and look at third-party temperature sensors as their problem, not ours, this day and age, people expect their smart thermostat to be able to pick up when their temperature sensors from third parties stop working. It's an expectation that, if you want to be honest, you would expect your smart thermostat to do. So, when do we do a true software root cause analysis? What do I mean by that? Sometimes we just deal with software apps. Sometimes we deal with hardware systems which are very, very reliant on software, and we might know from the start that the failures that hardware product is experiencing is due to software. Classic example that Anne-Marie talks about is a medical device where when people were pushing the abort button, which is something you do when a medical device is doing something, it was causing the entire system to stop. That might sound like the right thing to do, but it's not. In this medical device where it's taking samples, testing samples, sensing different things in samples, whenever you push the abort button, there are certain activities which need to complete first. You need to complete the full sensing protocol and then have those sensors go through calibration, cleaning, and storage. What the abort button was doing was stopping everything. And so when you asked it to do something else, the machine was in the wrong state and they had to manually pull everything out, pull the hand, redo the sensors, everything else. So it was a clear software failure, even though it was a hardware system, but people could see straight away it was a software issue. So that's when we start doing true software root cause analysis, where we exclude hardware. We do software only root cause analysis for big failures, where something goes kaboom and we know it's software, or we have lots of failures. In that medical device example, what the team was neglecting to do was to join the dots. Every ticket that was raised for this abort button not cancelling processes halfway through, it just got added to the list. No one was picking up that the abort button was doing this. No one could see the trend. And no one was saying, hey, we need to look at the software in this piece. Now, the best way to get around that scenario is to have a state diagram. A state diagram wasn't done, and so therefore the software engineers were not aware that the abort button shouldn't be taking the hardware from one state to another until those states were completed. So that's when you do essentially software only root cause analysis. But remember, these days software runs everything, which means that software ruins everything. So if you have a root cause analysis, do yourself a favor, focus on hardware first, and then focus on software during that initial brainstorming period. You could save yourself a recall, millions of dollars, embarrassment, a car manufacturer saying you passengers have forgotten how to sit in a passenger seat. I mean, come on, that seriously happened. That just shows how hardware-centric the root cause analysis team at Nissan was at the time. We've ruled everything else, therefore you guys have forgotten how to sit properly. True story. So, on that note, are there any questions about how software fails? Noting that that's a broad topic, and I may have not met expectations in terms of getting to nitty-gritty of specific details, but I find the very first thing we need to do when it comes to software is understand that it usually starts with the hardware team, the designers, not telling the software team what to do. Those simple coding errors, if they're the only issues we ever had, fantastic. Easy to find, easy to fix. But when we don't design the software properly, that's when it's really hard to find what causes that failure. If you want to ruin the reliability of your product, don't tell your software engineers what the system needs to do, or wait until they start doing their agile software development process and say, hey, I've got to tell you, you need to add this stuff. A lot of hardware engineers think software is just this permanently malleable thing that you can tell them, hey, just change this, do that, whatever, and it's not a problem. It's very lazy, it's very selfish. You need to look after your software engineers as much as anybody else these days, and that might mean you need to, before you start tearing into designing your product, take a deep breath, go through the software failure modes, work at the specifications, get your software guys in the same place as you, get the state diagram, all these wonderful things done, set them off on the right foot, And hopefully if that happens, then the only defects you'll have are those coding errors, which are easy to fix, easy to find and easy to fix. Any questions? Brian writes, wholeheartedly agree. A large number of the software failures I've seen can be tracked back to the software team being unaware of the hardware, how the hardware can fail to function properly. Fantastic, Brian. David writes, have you heard the rampant use of timing problem in this context? Yes, I have. I'm going to go back to Anne-Marie. She has compiled what's called the Common Defect Enumeration. It's available publicly through the Defense Acquisition University. Essentially, she has catalogued all known failure modes, software failure modes, and there's 10 software failure mode categories. One of them is error handling, which deals with when something goes wrong with the software. Another, and also with hardware as well. Another category is timing. So there's a whole category of software failure modes that, as in what is my software doing or not doing, which are linked to timing. And she actually has an enumeration where it's five symbols or groups of symbols in a row separated by hyphens. The first one tells you if it's an error handling or a timing problem. If it's T, it's a timing software failure mode. Sorry, I'm going to make my chat window bigger. Where do systems engineers fit in this process? Nate asked. That's a good question. Now, there are good systems engineers and there are bad systems engineers. The bad systems engineers are the ones who think we just need to get the specifications perfect, and then if anything goes bad, it's someone's fault. That's not mine. Now, there is obviously a need to try and get specifications done as thoroughly as possible up front, but it goes beyond that. Because when we talk about systems engineers often forget to deal with the bits of the specifications between hardware and software. So what do I mean by that? Systems engineers will tell hardware team, these are your goals, these are your targets, these are your specifications, hardware team, go do that. Software team, these are your goals, these are your specifications, go do that. It's the bit in between, what we call the interface specifications, which can run rampant. Going back to Anne-Marie's common defect enumeration, we have what's called entry points. How did that issue get into our code? The entry point for the HVAC system scenario we looked at was the design. So they didn't have a state diagram. That was how that fault was able to get in there. But the most rampant entry point are the interface specifications, where the hardware team doesn't tell the software team how that temperature sensor can fail, or what a faulty signal looks like, or what the vibration looks like from that idling engine. So from a systems engineering perspective, go back to that Nissan example. Systems engineers rarely are going to identify that the software for our airbag needs to be able to accommodate vibration from the idling engine as a passenger sits down. That's where you need that dialogue between the two groups. So systems engineering, which has this sort of very top-down approach, usually misses that sort of stuff. So a good systems engineer will know that their work is not done once they've got these high-level specifications. They need to know and facilitate those discussions between the hardware and software team before anyone starts writing or designing anything. So hopefully that answers that question. Zafar asks, as in the case of hardware, we carry out FMEA. What is procedure in case of software? FMEA again. In fact, the FMEA course I teach, I've got AI prompts which help us with each step of the root cause analysis in the FMEA process. And those prompts are able to leverage that common defect enumeration, which is available online. It is truly amazing what these prompts can identify in terms of potential software root causes of failure. So my smart lock, which is the central example for my FMEAs, when we do the FMEA itself and enhance it with AI, all these software failure modes are coming up as well, which are just not intuitive. It's very hard for people to imagine that at the very start. When we did that for our smart lock, the most problematic, the most risky failure scenario was a timing failure scenario with the keypad in the software. That was identified as the most likely, most problematic issue for that smart lock. And the good thing about AI enhancement is it can take your organization's procedures, lessons learned, historical data, and work out if your organization is good at software or not. So in this case, it said that's the most likely reason that your smart lock could make your company go bankrupt. And then the corrective actions, which is really simple. Do this, do this, do this, test with this, add this in beta testing, done. That problem will not happen. So for me, especially when you enhance it with AI, it's just so good if you have the prompts that can leverage into that CDE to make that software failure scenarios come up before you start designing. It's a good question though. Daniel says that yes, the CDE from Anne-Marie is excellent, highly recommend it. Thank you. Renee, what about software used in electric devices, PLCs, and automation, so programmable logic controllers? Yeah, so it's exactly the same. I'd say we tend to differentiate software and firmware. Firmware is software for this conversation. I know some people will be having epileptic fits by hearing that, but you have hardware and we have software/firmware. So firmware is obviously very tied to hardware. So PLCs are a great example. For example, what does your PLC tell your plasma cutter on an arm to do when the power goes out? What happens when the power comes back on? Great example, real world example. In some cases, the PLC and the programming behind it essentially restarts a job from wherever that plasma cutter stopped. So if the plasma cutter was in the middle of a piece, it restarts a job, ruins perhaps tens of thousands worth of steel. So it's the same applies to PLC. PLCs are good in that you sort of have this very hardware, software centric relationship presumes. And so it's a lot easier to get people on side when it talks about hardware. If that didn't answer your question, Renee, please let me know. Nasri writes, unlike hardware, it seems software failures don't follow the bathtub curve. Is that right? Well, software failures don't wear out at the back, so to speak. They definitely do follow the first part of the bathtub curve. The failure rate goes down if you're going through what we call defect discovery or debugging. And so if your organization is routinely debugging during defect discovery or from tickets from the field, then yes, you will see the failure rate tend to go down over time. There are some nuances there, especially if you have a relatively utilitarian device like a smartphone and your users start using it in different ways, and the failure rate might go up again because all of a sudden a function is now being used by more people, which is more buggy. But theoretically, yes, we have this decreasing failure rate, and during defect discovery, we know that decreasing failure rate tends to have a negative slope of 0.4 when plotted in log-log scales. Carl Wright, problem solving, whereas bad systems engineers operate in silos, neglect documentation, and apply short-term fixes that create larger systemic issues. Any thoughts? Hopefully my question to answer to that previous question resolve that. Nate, yes, thank you. I think that's, sorry, I'm glad that what I came up with worked. Carl writes, over-engineering and shortcuts. Any thoughts? Proactive automation and process. Any thoughts? Sustainable problem solving. Any thoughts? Continuous learning. Any thoughts? I'll come back to those because continuous learning is great. There's a lot of things there. Carl writes again, hardware failures involve physical damage or wear to device parts, while software failures stem from code bugs, corrupted data, or system logic errors. Any thoughts? Yes, you've listed a few of the reasons why software can fail. There's quite a few more than that. So those categories, those 10 categories of failure modes, I'm going to try and do my best to remember all of them. There's error handling. So what does your software do when a problem ramps up? You need to have that state diagram, what we call error states, where the software goes to when it realizes something is wrong. Timing, data description. A classic example, all those NASA spacecraft which have impacted the Martian surface or gone somewhere else because one software program was written using imperial metrics, while the other was using international standard metrics, i.e. foot-pounds versus Newton meters. Machine learning is another one. Algorithms, so that Nissan issue where it didn't detect that passenger sitting in, that's an algorithm software failure mode. Good Lord, I've forgotten what I've said in terms of those software mode failure categories. There's 10 of them. What else? I can't remember all of them. But yeah, there's quite a few. Users on Quora. Cool. So that's you can take that any agreement to the bank. Agree that hardware failures often worsen over time due to physical degradation, whereas software bugs are triggered unpredictably by specific data inputs or code interactions. Any thoughts? It's not an easy question to answer because yes, it is. The term random is grossly overused in many scenarios. When in that text there, Carl, when people say random in that context, it sort of suggests that software can fail on any given day at any point in time with any given likelihood, and that's not true. Failure is always random, whether it's wearing in, wearing out, or anything in between. And so when we have that decreasing failure rate, that's still random failure. They're occurring randomly, but the pattern shows that the failure rate is decreasing as you go through debugging and discovery and debugging. So that said, if there is a sort of latent functionality in your product that some subpopulation of users then start to use more often than others, well, that would then see the failure rate increase and may then satisfy that criteria of being random. A good pseudo example are cell phones, mobile phones. You might remember those original mobile phones that came out, those big bricks that cost thousands of dollars. When they were initially manufactured, it was believed that the clientele would be the luxury clientele, the upper class, the very wealthy. It turns out the first most profitable market segment were tradespeople. Why? Because electricians could have this huge, expensive mobile phone in their truck, go to a job, and instead of having to go back to the office to work out where they need to go for the next job, just call the office, say, okay, I need to go where, drive straight to the next place, and the time and money saved more than offset the cost of those very expensive mobile phones. So a ton of those early manufacturers disappeared because they developed phones for the luxury market, which weren't particularly robust. And the only manufacturers that remain were those who quickly realized we need to make these phones robust because plumbers and electricians and carpenters, they're not going to deliberately mistreat it, but they're sort of going to throw that phone around in a toolbox. And so those early mobile phones, software was a key part of it as well, but that's an example of where we think it's going to be used in this way, but it turns out to be used in that way. And that's possibly the closest we can come to random. All right, so got through those questions. Carl asked to talk about over-engineering and shortcuts. That's a broad topic, but for software failures, I don't think over-engineering applies. I could be wrong. If any software engineers are out there, they might have seen people who write too much code. Actually, to be fair, I know we're coming up on time. I often use the example of Netflix. They create these programs. They give them the Chaos Monkey, Chaos Gorilla, Janitor Monkey. They got these monkey and ape names. Together, these programs are called what they call the simian army. And their software engineers need to write code that can withstand these constant attacks from these different programs. And so the Janitor Monkey, for example, will remove code if it isn't used for a long period of time. Why is that important? Well, it just means that if you've got 10 relatively similar problems or functions your software needs to handle, what you don't want to do is write 10 subtly different programs to do that. You want to have one program which can deal with all those different or 10 slightly different problems or functions to solve. So you have one set of code which can make very robust, and if there's any problems with that, you can fix it and it fixes all 10 problems. If you have to have 10 slight variations of the same program in your software, that's just a nightmare. So Maybe that classifies as over-engineering. Proactive automation in process. I think, again, that's a very broad topic. I would talk about the term proactivity. People believe you cannot talk about software until after you have got the hardware configuration sorted out, and that's not true. For example, if you're designing a smart lock from scratch, you're a startup company, never designed a smart lock before, this is the first smart lock you're going to develop. You know it's going to have a handle, a keypad, Bluetooth connectivity. It's going to have an electric motor turn and push the bolt in and out, so on and so forth. You know these things. It's going to have batteries. The batteries need to be on the inside. So before you start designing, you know essentially what the configuration is going to look like, even if you haven't got the dimensions yet. And there's no reason why you can't talk about timing errors for keypad entry before you start designing the keypad. No reason. But I think psychologically, a lot of us think we have to design the hardware first. The software engineers can come in and make it all work. That's a terrible idea. Sustainable problem solving. Hopefully all problem solving is sustainable. That's all I can say about that. About continuous learning. I think broad topic. In the world of software engineering, though, I'd suggest what we fail to continuously learn, that telling the software engineers what they need to do too late in the process is simply not good enough. It just destroys reliability. And I think 3 minutes past the hour, I have answered all the questions to varying degrees of success. Any more questions before we call it quits for this one? Got a few thank yous. Thank you for those thank yous. So I think we're done, Fred, unless someone's got a last minute brainwave. If you think of any questions later on, you've got our contact details. Feel free to reach out.